Welcome to this presentation. My name is Leo Heimbach and I'm a PhD student in the Distributed Computing Group at ETH Zurich, and I'm very happy to present here at the FC-DeFi workshop. So the work that I will present here is an empirical study of market inefficiencies on Uniswap and SushiSwap, which are two decentralized exchanges on the Ethereum blockchain. And this work was done in collaboration with Jan Berg, Robin Fritsch, and Roger Wattenhofer. So decentralized exchanges have recently emerged as smart contracts on the blockchain, mainly Ethereum. And what they allow is they allow users to trade cryptocurrencies without involving any financial intermediaries. So what we focus on is a subclass of decentralized exchanges in this world, which are constant product market makers. Most decentralized exchanges on Ethereum, the Ethereum blockchain function as constant product market maker, or at least a variation thereof. And Uniswap v2 and SushiSwap, which we study in this work, are constant product market makers. So what the constant product market maker does is that it aggregates liquidity in what is referred to as liquidity pools for every cryptocurrency pair. So here we have a liquidity pool between Bitcoin and Ether. And now if Alice wants to exchange Bitcoin for Ether, she can directly do this with the liquidity pool by interacting with the respective smart contract. And in the entire process, there's no need for any financial intermediaries. Rather, her trade executes automatically. So now in the case of a constant product market maker, trading happens along the price curve, which is drawn here. So here we draw a price curve specifically for pools with token X and token Y. And the price curve is defined such that the product of the two amounts of tokens stays constant, hence the name of the market. So we will now look at an example trade in such a market. And let's consider a trade between tokens X and Y, and the current pool status is indicated. So at the start, the pool holds 90X and 180Y. This means that the current price is 1X for 2Y. Now the trade wants to exchange 30X for tokens Y, and the trade executes along the price curve, and the trader would now receive 45 tokens Y for the 30 tokens X. Note here that we also have to mention that liquidity providers receive fees for every trade that goes through the pool. And in the case of Uniswap v2 and SushiSwap, this is 0.3%, which is charged on the input amount of each trade. So in reality, the trader needs to be putting in an additional 0.09x to receive the 45Y. Further, we also notice here that even though these markets are referred to as constant product market maker, the product in fact does not stay constant in reality, rather the product increases steadily, as the fees are also fed back into the market, into the pool. I also mentioned earlier that at the start, the price of the pool was 1x for 2y, but this is not what our trader received. And this is a result of every trade in a constant product market maker having an expected slippage, which is an expected decrease in price based on the trade size as well as the pool's liquidity. So the more a trade moves the pool across the price curve, the higher the slippage will be. So in our example, at the starting state of the pool, 1x was worth 2y, but the trader only received 4y for 3x's. Which is quite a significant difference as the trade size was so significant in comparison to the pool's liquidity. So now we had a simple trade between tokens X and tokens Y. But if we want to exchange two cryptocurrencies, there's not only one way for a user to do this. In fact, there are very many ways a user can do this, as the user can route the transaction through any combination of existing liquidity pools. So let's consider the following graph consisting where the nodes are cryptocurrencies. So we have Ether, USDT, and Bitcoin, and the edges between them are liquidity pools. So the edges connecting two of the nodes are liquidity pools. Now Alice still wants to trade Ether for Bitcoin, and there are multiple ways for her to do this. So the most straightforward way for her to do this would be to send a transaction through the pool between Bitcoin and Ether. And then Ether is exchanged for Bitcoin in the pool. However, in the end, Alice then receives the Bitcoin she wanted. However, this is not the only way that Alice can exchange Bitcoin for Ether. She can also Ether for Bitcoin. She can also first exchange Ether to USDT, then USDT to Bitcoin, and also receives the Bitcoin she wanted. Note that here now she's using two liquidity pools, so she's paying the pool's transaction fee twice, but she might still receive a better price if the liquidity is better or if the prices between the pools are unsynced. Finally, there are also different decentralized exchanges on the Ethereum blockchain, and thus there might be various liquidity pools between the same cryptocurrency pair. So here we now show two liquidity pools between Ether and Bitcoin. And Alice can also now choose which pools she wants her trade to execute in, as one of them might offer an exchange rate. The exchange rate of these pools is not necessarily the same. So what she can do is she can also use the second pool to exchange Ether for Bitcoin. And we really saw here that there are now various ways for Alice to exchange her Ether for Bitcoin. And we only represented a very few number. There would be many more in reality. Now, Alice, of course, would like to get the best price for a trade. And in the mature markets, at least when we disregard fees, she should, independent of the venue she chooses, receive the same price, which would then be a sign that the market is efficient. Now, what we did in this work is we wanted to see how efficient these decentralized exchanges are. And for that, we empirically studied market inefficiencies on Uniswap v2 and SushiSwap. And a market is considered efficient when the prices of the market reflect all relevant information. So what we did in this work is that we specifically identified market inefficiencies and studied how they evolved over time. So for one, we looked at past trades and analyzed if they executed suboptimally. So we looked at trades on both Uniswap and SushiSwap. That is in particular that we identified which trades executed suboptimally, so which trades would have received a better price with a more complex routing, for instance, as this should not happen in an efficient market. And the other thing that we identified is cyclic arbitrage opportunities. So cyclic arbitrage opportunities result from temporary price inaccuracy. And what can happen is that if these prices are temporarily inaccurate, it is possible for a trade to execute in a cycle between the three currencies here and have a net profit. So price differences are the root cause of both suboptimal trades as well as cyclic arbitrage opportunities. And these price differences reflect that the market does not have the ability to reflect all relevant price information and indicate that there are market inefficiencies, which is why we looked for both these as a sign of market inefficiencies. So now we start by analyzing how many trades executed suboptimally in Uniswap and SushiSwap. For that, we restricted the analysis to large trades that were over $30,000 US. The reason why we did this is that these large trades allowed us to look both for price inaccuracies as well as a potential lack in liquidity in the pools. So we did our analysis between September 2020 and January 2021 and considered trades between 5 mature cryptocurrencies, so their price is known. We have Ethereum, USDC, USDT, DAI, and Bitcoin on both Uniswap and SushiSwap. And now the number of large trades that there were in the time frame that we looked for is shown on the edges between the cryptocurrencies for both Uniswap and SushiSwap. And in a total, there were more than 100,000. And we now checked how optimal their routing was. And these were just simple trades. So they only used one pool between the cryptocurrency pair. So to figure out whether these trades routed suboptimally or they could have routed better, we constructed a set of independent paths between the 5 tokens. So if we had a trade between USDC and Ether, we on the direct route included both the Uniswap and the SushiSwap path. But on the other routes, we initially only included the more liquid paths, which were pools, which were always the Uniswap pools. Note that in the graph that is shown here, the solid lines are Uniswap pools and the dashed lines are SushiSwap pools. So for paths containing, so the reason why we chose to use these independent paths instead of the entire graph, that it's much simpler to compute the optimal routing in such a network. And what we found is that almost a third, so 27% of trades were optimizable using this network. And on average, it was possible to increase the output amount of a trade by 0.15%, which might not seem like much, but this is an invisible tax that traders are paying for market inefficiencies. So now we also wanted to check whether these market inefficiencies stem from price inaccuracies or also maybe a potential lack of liquidity in the market, which is why we initially picked the larger trades. And for that, we also looked how many paths these optimized routings were using. So you can also split your trade for many paths. You don't need to execute the entire trade along the same path. And we found that most optimized trades were only using 2 paths. So 3/4 of all optimized trades were only using 2 paths. And this is a sign that these market inefficiency largely stem from unfavorable prices instead of a lack of liquidity. However, for a small proportion of trades, they were also using 3 and more paths. And in these cases, it might also be a lack of liquidity that leads to these suboptimal trade executions. So now we also then repeated the same analysis to include the less liquid pools, so the SushiSwap pools, in the set of independent paths. So now here again, we have a different network in which we were searching for optimized trade executions, where again, the SushiSwap paths are the dashed lines and the Uniswap paths are the solid lines. And we saw that when we combine both platforms in this new network, we were able to optimize an even larger proportion of trades, which was more than 33%. So using this network, 33% of trades were optimizable. And further, the average gains, as is shown in this table here, were also slightly higher with using the less liquid pools than with only using the more liquid Uniswap pools. So it appears that it's more price inaccuracies rather than low liquidity, which lead these trades to execute suboptimally. Okay, then we also looked for cyclic arbitrage opportunities as a sign of market inefficiencies. And for that, we first analyzed the occurrence of cyclic arbitrage opportunities between August 2020 and January 21, only between Ethereum, USDC, and USDT. And these 3 cryptocurrencies have the largest pairwise pools between them on Uniswap. And here now in this plot, we plot the weekly number of blocks with arbitrage opportunities. And we were able to see that most arbitrage opportunities are between August and September of 2020. And this is really a time where the volume of Uniswap exploded. It increased by 700% within 6 weeks. But after this initial volume explosion, the cyclic arbitrage opportunities become much less. So we also observe now a second trade when we compare the daily arbitrage opportunities to Ethereum's price movements on a given day. So after the initial explosion of volume in the summer of 2020, we find that on days with exceptional high price movements, we observe very many arbitrage opportunities. So if you look at the second part of this time frame, then on days where we have very high price movements, we also see more cyclic arbitrage opportunities. However, over the entire time frame, the correlation is only 0.15, and thereby relatively low. So what we then did is that we again searched for cycles on both Uniswap and SushiSwap now, and again between the 5 cryptocurrencies, so Ethereum, USDC, USDT, DAI, during 2 different periods. The first period was between September and October of 2020, and the second period was between December 2020 and January 21. So the networks that we use to search for the cyclic arbitrage opportunities are shown here. Again, the dashed line are SushiSwap pools and the solid line are Uniswap pools. So in the first period, the price of Ethereum was relatively stable. It moved by less than 8% over the entire period. However, in now the second period, the price of Ethereum was highly volatile and Ethereum more than doubled within this time frame. So now, as we expected in the first period where the cryptocurrency prices were quite stable, there were only 84 blocks in the 140,000 that we looked at that had cyclic arbitrages in them, and their mean profit was 0.24%. So it appears that these stable cryptocurrency prices do not allow for very many cyclic arbitrage opportunities, as the markets seem to be able to sink their rates quite well. However, now in the second period, where we saw these very volatile cryptocurrency prices, we find that more than 1,000 blocks had cyclic arbitrage opportunities in them, and on average they had a higher profit of 0.35%. So as we expected, the number of cyclic arbitrage opportunities is significantly higher in the second period that is characterized by highly volatile cryptocurrency prices. So now we again plot both the distribution of arbitrage opportunities over time, so on each day in the second period that we looked at, as well as Ethereum's price. And we find that more than half, in fact, of all cyclic arbitrage opportunities occurred on the 4th of January and 11th of January, so only on 2 different dates. And on these dates, the Ethereum price experienced temporary price movements exceeding 20%. So it seems to be that the market is not able to adapt to these very volatile cryptocurrencies sufficiently fast. And the correlation here between the cyclic arbitrage opportunities found and Ethereum's price movements was 0.72, which is a very significant correlation. So it appears that the floating exchange rates on Uniswap and SushiSwap, so in their pools, simply cannot adjust to the market prices sufficiently fast. So this brings us to the conclusion of this presentation, and we found that traders are experiencing market inefficiencies on decentralized exchanges. In fact, we saw that around 30% of the analyzed trades executed at unfavorable prices. And we were also able to show that this is largely due to price inaccuracy rather than the market's liquidity. We also see that the market struggled to reflect external prices in the beginning phases, so during the initial volume explosion. However, then the market adapted quite quickly and price inaccuracy largely disappeared. Now these market inefficiencies are generally on days when cryptocurrencies are highly volatile. It seems that parts of the market do not adjust to external price changes properly and not fast enough, and this does create cyclic arbitrage opportunities even now. So with that, I thank you for your attention.